In this video, we're going to cover section 7.3 on bimolecular reactions, specifically the SN2 and E2 reactions. We'll start by discussing the substitution reaction. And the substitution reaction involves two of the four patterns, the arrow pushing patterns, that we discussed in the previous lectures. Now, the two patterns that are most important in substitution are the core steps in every substitution reaction will be nucleophilic attack and loss of a leaving group. Now, the order in which these steps occur depends on the specific type of substitution mechanism. And we'll use two terms to describe these types of mechanisms. There's the concerted mechanism, and in a concerted mechanism, these two arrow pushing patterns are occurring at the same time. They're occurring simultaneously, meaning that as the nucleophile is attacking the partial positive charge on a carbon center, the carbon leaving group bond, or in this example, the carbon X bond, is starting to break. So as the nucleophile carbon bond is starting to form, the carbon leaving group bond, in this case X, is starting to break. Now, the other types of mechanisms that we'll often observe, and specifically for substitution, another version of substitution involves what's referred to as a stepwise mechanism. Now, in a stepwise mechanism, you have first the loss of the leaving group for this type of substitution mechanism. That leaves you with an intermediate carbocation, and then following the formation of that carbocation, we can have nucleophilic attack. So the difference between these two mechanisms, both concerted and stepwise, is that in a concerted mechanism, we have a single energy barrier, a single transition state. Whereas in this stepwise mechanism, we have two transition states. One transition state, one barrier going from this alkyl halide to the carbocation, which forms that as an intermediate, and then the intermediate overcoming yet another barrier through another transition state to our final product. So we refer to this as stepwise because there is more than a single step. There are two steps involved in this particular mechanism. Whereas in the concerted mechanism, these two arrow pushing patterns occur within a single step, a single transition. So let's start by looking at SN2, and then we will follow this up with an elimination reaction known as E2. In a future video, we'll look at SN1 and E1. And again, I'll explain these terms, but these designate specific substitution and elimination reactions in which alkyl halides undergo. So we'll start with SN2. As you can see, as shown here, the SN2, this is an abbreviation in many ways, which describes a particular mechanism for alkyl halides. S involves substitution, the N stands for nucleophilic, and the number 2 refers to a bimolecular process. Now, substitution, as we've talked about previously, what's going on here is we have a net change in the reactant to product state, and that net change is the substitution of this atom X for the incoming nucleophile. Nucleophilic implying that there's a nucleophile involved in this particular mechanism, and bimolecular means two molecules. And so the two molecules that are interacting in the single transition state that is involved in this mechanism is the substrate, which is the alkyl halide, and the incoming nucleophile. And so that's where this abbreviation SN2 comes from. It's nucleophilic substitution, bimolecular, implying that you have two molecules involved in the rate determining step of this reaction, We don't need to go into specifics regarding the kinetics, but that's where the term is coming from, that two molecules are involved in the most important step in this mechanism. And as shown, this is the only step in this mechanism. So therefore, it must be the important one. Now, if we want to rank the relative reactivity of alkyl halides with respect to the SN2 reaction, we have to look to the number of substituents that are bound to the alpha carbon. So we've talked about the alpha carbon term previously. The alpha carbon is the carbon directly attached to the leaving group. And for alkyl halides, that leaving group is a halide. Now, as you can see in this diagram, the most reactive alkyl halides are the methyl halides, followed by the primary alkyl halides, secondary alkyl halides, and the least reactive, or in many ways, the unreactive species for alkyl halides are the tertiary. And the reason for this correlation of substituents to reactivity has a lot to do with steric hindrance. So as you may recall, when we talk about steric effects, we are referring to atoms trying to occupy the same space. And they don't do that very well. And so the example that you want to be thinking about here is we have this incoming nucleophile. This nucleophile is wanting to share its electron density with the partial positive charge on the alpha carbon. But if that alpha carbon is surrounded by substituents, access to that alpha carbon is going to be hindered. And so steric hindrance implies just that the ability of the nucleophile to overlap its orbitals, its hybridized orbitals, onto the sp3 hybrid of carbon is going to be very difficult. And so as a result, the tertiary alkyl halides are unreactive via the SN2 mechanism. We don't see any reactivity via SN2 for any nucleophile, regardless of its strength, with the tertiary alkyl halide. Now the situation gets a little bit better when you reduce the number of substituents to 2 around the alpha carbon. There is some reactivity via SN2, but there still is some hindrance associated with those additional methyl groups. We really start to see the best reactivity with primary systems. So primary alkyl halides and methyl halides, these are going to be the most reactive substrates. And when I refer to the alkyl halides, I'll refer to them as a substrate. But they're going to be the most reactive towards other nucleophilic reagents or nucleophiles. So methyl and primary systems are the most reactive, and those are most commonly observed in these SN2 reactions. And here's a table showing you the relative effect of substituents on the rates of reaction. And you can see that for the tertiary system, this tertiary bromide, this tertiary butyl bromide, the rates are really non-existent. Secondary system, a little bit better, but still quite small relative to the primary system. So if the primary system has a rate, if we normalize it to 1, we're seeing that less than 1% reactivity, relative reactivity with the secondary system. Beta substituents also can have an effect. We're going to primarily focus our discussion on the effect of alpha substituents, but yes, if you have substitution around the beta position, even though the beta carbon is not involved in the mechanism, it does in a sense provide some steric hindrance to the neighboring alpha carbon, but the effect is minimal relative to the effect of alpha substituents. Now, the relative energy of a transition state determines the rate of a reaction. If the transition state energy is high, then the activation energy will be high, as shown by this barrier, this height from reactant to the transition state. Now, if the transition state is low in energy, then the activation energy will be low and the rate will be fast. It will be faster compared to a situation where that barrier is high. So using energy diagrams, we can compare the relative rates of reaction by comparing, in many ways, the height of these barriers. And these barriers reflect the activation energy, and we said that a high activation energy will lead to a lower rate of reaction. And so we can use absolute values, measurements that we make in the lab, to compare the relative rates of reactions. We can also use energy diagrams as a pictorial view of those same rates. But as you can see, as we increase the number of substituents around the alpha carbon, the rate of the reaction via the SN2 mechanism will be reduced. So in addition to the nature of the substrate, SN2 substitution reactions are also dependent upon the relative strength and concentration of the nucleophile. And as we showed you in section 6, here is a table listing the various nucleophiles that we commonly use in substitution reactions. And what I've done is I've tried to rank them from the very good to the weakest. And so as you may recall from earlier videos, that the polarizability and size of the hydrosulfide ion, the alkyl sulfide ion, and the iodide make these species very good nucleophiles. In addition, second row elements with formal charges of -1 are also quite good as nucleophiles. And here we also have the bromide in that same entry. Nucleophiles that are not so good or not as good as the ones we've just discussed are the neutral versions of many of those found in entries 1 and 2. And then finally, our weakest nucleophiles are alcohols and water. And so by ranking the relative strength of these nucleophiles, it shouldn't be a surprise that when we compare the relative reactivity of the same substrate undergoing reaction with a strong versus what we refer to as a weak nucleophile, that the rates of the reaction will also be dependent upon their relative nucleophilicity. So when we compare the relative rate of reaction of a weak nucleophile, water, to that of its conjugate base, which is the stronger nucleophile, the hydroxide ion, we expect that the rate of the reaction will be much faster for the hydroxide ion, given its stronger nucleophilicity. Whereas the opposite is true, that water being a weaker nucleophile, although the reaction may go for the most reactive of the alkyl halides, the methyl halides, the reaction will be quite slow. Now, the last aspect that we must consider when discussing the relative rate of a reaction via the SN2 mechanism is the choice of solvent. So we will categorize polar solvents into two groups. We have polar protic solvents and polar aprotic solvents. Now, protic and aprotic refer to whether or not the solvent contains a hydrogen atom bound to an electronegative element. So a polar protic solvent is shown in this table. Here we have water and alcohols primarily, but also ammonia and acetic acid. But definitely water and the alcohols are the most common polar protic solvents used in substitution reactions. Now, polar aprotic solvents, these are solvents that don't have hydrogens attached to electronegative atoms. So you may be asking, why is that important? Well, when you have a hydrogen atom attached to an electronegative atom, it allows for potential hydrogen bond formation with other species. And so polar protic solvents are good hydrogen bonding solvents. They will bind to nucleophiles through a hydrogen bonding type network. Whereas polar aprotic solvents, because they lack the presence of a hydrogen attached to electronegative atom, they are not involved in any kind of hydrogen bonding. And so as a result, the polar aprotic solvents are preferred in the SN2 mechanism because these solvents will not interfere with the ability of the nucleophile to attack the alpha carbon of your substrate. Whereas protic solvents, like water and the alcohols, these can form solvation spheres where they can solvate a particular nucleophile, and in a sense, they're preventing the nucleophile from reacting with the alpha carbon in an efficient manner. So in terms of the polar aprotic solvents, it's good to familiarize yourself with acetone, dimethylformamide, which is shortened as DMF. Acetonitrile is also a good solvent as a polar aprotic. And finally, dimethyl sulfoxide is also a good solvent. We won't mention this one very much, but you may see it on a future assignment. But the four most common polar aprotic solvents that are discussed in this textbook are acetone, DMSO, DMF, and acetonitrile. In terms of the protic solvents, again, I will typically revert to your water and your alcohols like methanol and ethanol. Yes, acetic acid and ammonia as well, but I must admit a lot of examples will include these particular solvents. And so we can see the effective solvent in this table. Table 7.3 looks at the rate of reactions of an SN2 reaction with iodomethane and comparing the relative rate of reaction of these halides in different solvents. And so you can ignore the fluoride example. Fluoride chemistry is a little bit exotic, so we're going to ignore that for the most part. But if we look at iodide, bromide, and the chloride, you can see how, yes, the rate of the reaction is going down, and that's more or less reflected in the relative strength of these species as a nucleophile. So if we go back to the table, polarizability has a large part to play in the relative rates of the reactions. But if we compare the relative rates in methanol, MEOH, to that in dimethylformamide, DMF, you can see that for the bromide species, the rate is over 20,000 times greater in a polar aprotic solvent than it is in a polar protic solvent. So the protic solvents, the rates of these reactions are relatively slow, quite slow, compared to the relative rate in polar aprotic solvents. And so you can see, even for the best nucleophile, you have a 100-fold, factor of 100-fold, 2 orders of magnitude greater rate of reaction in the presence of DMF as opposed to methanol. And so here is the type of image that we think about when talking about the interaction of solvent with our nucleophiles. And so these X's implying that there is no interaction or strong interaction between dimethyl sulfoxide, DMSO in this case, with the chloride ion. And it's just there are no hydrogen bonds available, and as well, the partial positive charge associated with the sulfur atom, it's restricted, it's sterically inaccessible to interacting strongly with the chloride as well. And so if we compare the relative energy associated with the SN2 reaction, when we compare the solvent that is chosen for those reactions, we see that the barrier is much lower for polar aprotic solvents than for protic solvents. So polar protic and polar aprotic, no hydrogen bonding ability, no interaction or very little interaction with the nucleophile. That allows the SN2 reaction to occur at a much faster rate, whereas we have a polar protic solvent which is capable of forming hydrogen bonds with the nucleophile, in a sense solvating them, that makes it more difficult for the SN2 reaction to occur. And so as a result, the energy barrier is going to be significantly higher. So to finish this video, we'll discuss the E2, the elimination reaction, which is also concerted. And so that's why the text in our video discusses the SN2 and the E2 together, because they both have this concerted mechanism associated with them. Nonetheless, every elimination reaction exhibits at least two of the four patterns. So at the core of elimination, there will always be a proton transfer and loss of a leaving group. And so as you can see in this example, in the concerted mechanism, the elimination reaction involves a base. And the first part of this mechanism is the base undergoing a proton transfer. So the base is accepting this hydrogen atom as a proton in a proton transfer reaction. What's also happening is the second curved arrow is showing that the electrons of this carbon-hydrogen bond are going to become a new pi bond. And as this pi bond is starting to form, this leaving group carbon bond is starting to break. And so there's three curved arrows to represent these two arrow pushing patterns. We have the proton transfer, the electrons of that bond becoming the new pi bond, and the breaking of the alpha carbon leaving group bond. And so the net result of the E2 elimination, this concerted mechanism, is the formation of an alkene. Now we also have a stepwise mechanism for elimination, and that's shown below, where we have first the loss of the leaving group. So this carbon leaving group bond will break. That leaves us with leaves us with a carbocation intermediate, and then that carbocation intermediate will undergo reaction with the base. So the loss of the leaving group occurs first to form this intermediate carbocation, and then there is a proton transfer in which the base is involved. And as a result of this reaction, we have the formation of an alkene as well. So every elimination reaction will involve both a proton transfer and the loss of the leaving group. It's a matter of whether or not they occur in a concerted manner or a stepwise manner. So in the concerted mechanism for an elimination reaction, a proton is removed from the beta position and the leaving group is lost from the alpha carbon. And the new double bond that will form, the new pi bond, will form between the alpha and the beta positions. We call the concerted mechanism for elimination E2. E standing for elimination and 2 representing bimolecular. So again, in the transition state, there are two molecules that are involved in that transition state, the base as well as the substrate. And so again, you can see our arrow pushing pattern for the E2. Base is going to remove a hydrogen as a proton from the beta carbon. The electrons of this carbon-hydrogen bond as shown, they will become the new pi bond, the electrons of the pi bond between the alpha and the beta carbon, and the carbon leaving group bond will break. So in terms of the aspects that are important to consider with the E2 mechanism, they are fewer than what we saw for the SN2. For E2, what you really need is a strong base. And so, yes, there may be competition from other reaction mechanisms, i.e. SN2, but the nature of the substrate is less important as we saw for SN2. So in the example of SN2, we saw that the tertiary alkyl halides were virtually unreactive towards any incoming nucleophile. That's not the same situation when we refer to elimination. So as shown in this figure, if the hydroxide is your nucleophilic species, or in elimination, your basic species, we said for a tertiary alkyl halide, the chances of the hydroxide actually substituting for the leaving group is very, very low, almost non-existent. And that's due to the fact that this alpha carbon was too sterically hindered by the 3 substituents around it. Whereas for the E2 elimination reaction, it's not important for the base to actually interact with the alpha carbon. It doesn't do so. It's only interacting with a hydrogen that's bound to a beta carbon. And so as a result, there is less steric hindrance associated with that proton transfer reaction. In fact, there's no steric hindrance associated with the interaction of that hydroxide with this hydrogen off the beta carbon. So tertiary substrates, they will undergo the E2 reaction quite rapidly, but basically we will not see this for the SN2 reaction. So again, substrate has some role to play in SN2 reactions. We saw that effect, but the same effects are not observed for the E2. It's the nature of the base which is most important in the E2 mechanism. So I'll leave you with a cartoon that discusses the E2 reaction, maybe a good way to recall it. And with that, I will sign off. You are more than welcome to contact me via email if you have any questions about SN2 or E2, and we can set up an appointment via Zoom if necessary. Thank you.